Well, first of all, congratulations to Tony Leggett, and very warm thanks to the organizers of this wonderful meeting. This morning, when Urvashi and Deepankar described some of the early consultations they had that led to this meeting, and later from the other very nice and stimulating talks we had, I started thinking how wonderful it is for one person to combine high standards of science and high standards of humanity. So we certainly celebrate that with everything we have. Now, I begin, and I shall use Raphael Sorkin's diagrams also. I begin by discussing the various historically discussed signatures or markers of quantumness. One of the earliest one is the fact that if you are going to associate a wave function to a particle, is it not problematic, as discussed by Schrödinger and Einstein, etc.? Is it not problematic that the wave packet most often expands rapidly with time? The second signature of quantumness came through the efforts of Eugene Wigner in 1932, where he made an attempt to do many things, but in particular to write a joint distribution of position and momentum, which integrating over momentum would give you the correct quantum position probability densities, and similarly for the momentum probability densities. And the signature of quantumness that emerges is the fact that the Wigner function is not everywhere positive. So the Wigner function is not like a probability density in classical mechanics. And let me say the third signature that I will touch upon is the one that came through the 1935 paper of Einstein, Podolsky, Rosen, and perhaps more importantly, the 1964 paper of John Bell. The discussions of violations of local reality in quantum theory. Now, it is probably known by many people that these markers of quantumness are very different from each other. I will concentrate on a few very simple cases, simple examples in continuous variable systems to discuss these differences. I would like to begin by something which is somewhat inspired by the subject of this symposium, to talk about some time-dependent correlations which were discussed by Bell, not in his earliest paper, but much later. Well, let me emphasize that although Bell called his paper the Einstein-Podolsky-Rosen paradox, he never used the Einstein-Podolsky-Rosen wave function in his arguments. The EPR wave function was supposed to be an eigenfunction of both Q1 plus Q2 and P1 minus P2, two commuting observables. But there are problems with this wave function. So this problem, for instance, the wave function I have exhibited is an eigenfunction of q1 minus q2 with eigenvalue minus q0. And I didn't write the constant term, which means that its total momentum 0, p1 plus p2 equals 0. This eigenfunction, this wave function was never used by Bell. Now, presumably, one reason that is hitting you in the face is that this wave function is not normalizable. So, curiously, nevertheless, he returned to it in 1986, just 3 years before he passed away. He returned to this in 1986 in a paper that he called EPR correlations and EPW distributions. EPW are the initials of Wigner. To say that the EPR wave function has no non-locality problem. This is a quotation. And then Bell went on. So in other words, this is, I think, non-trivial. Had he used the EPR wave function, he would not have found the results that he found with the Bohm version of the EPR paradox. So Bell then obtained local reality inequalities on correlations between commuting observables which correspond to position measurements at different times. Now, one of the reasons perhaps to discuss this is that this argument of Bell is quite interesting because it can be extended to more general observations, even those which include spin variables, and experiments which I think can be reasonably easily done in various labs we have. So Bell showed that although the EPR wave function, he claimed, does not violate non-locality, there are wave functions for continuous variable systems which do violate the locality. He gave an example of a wave function which in fact violates the positivity of the Wigner function. We shall see in a moment. And I have to run through this because, partly because it is reasonably familiar, and partly because I have to save some time to discuss the new result we have. So suppose we have two commuting observables. I'm sorry, I pressed the wrong button. Suppose we have two observables, A1, A2. For example, Q1, Q2 for the two mutually commuting position operators, and two operators H2, H1, for instance, P2 square over 2M2 or P1 square over 2M1. So A1 commutes with H2, A2 commutes with H1. So here are the set of commutation relations. Then you can, as one does when one discusses the Heisenberg representation, you can define these operators A1 of T1 and A2 of T2. And you can see that these unitary transforms of A1, A2 also commute with each other. The correlations between these two commuting operators in the initial state psi can then be written in terms of a two-time wave function. So this is just an identity, very easy to check, that the expectation value of A1, T1, A2, T2 is the same as the expectation value of the time-independent observables A1, A2 in the two-time state psi T1, T2, where psi T1, T2 is simply defined in this way. You can, maybe it's worth noting, as Bell did, that these unitary transforms of Q1, Q2 are just these operators, Q1 plus T1 P1 over M1, Q2 of T2 is Q2 plus T2 P2 over M2. You can see that these two are also commuting observables. And the probability density for observing Q1 at time t1 and Q2 at time t2 is given by the two-time wave function in this way. Then he went on to remark that the two-time probability, that this probability density is the integral of the two-time Wigner function, which is constructed in the same way as the usual Wigner function. Just replace psi by psi t1, t2. And not surprisingly, you find that this two-time Wigner function obeys these simple differential equations, which means that the T1 dependence of the W of the Wigner of this Wigner function comes entirely in the combination Q1 minus T1 P1 over M1, and similarly for this one. So this very simple calculation shows that irrespective of any very detailed arguments, if the W initially is nowhere negative, then this situation will continue for all time. So let us say, let us simply tell you the remaining story of John Bell. A formal use of the impossible EPR wave function, impossible because of non-normalizability, is that this corresponding, that the corresponding Wigner function is also non-negative. It's a product of two delta functions. Of course, as I said, you can say that it's an impossible function. However, Bell then concluded from this statement, that the Wigner distribution provides a local classical model of the correlations, because it is everywhere positive. This conclusion is robust because the impossibility is easily remedied by using a regularized EPR wave function, which is very common in quantum optics. The two-mode squeezed vacuum state of quantum optics, where A1, A2 are the annihilation operators for the two modes, and zeta is a complex number. This state has the explicit expression which I show here in terms of the squeezing parameter R, and choosing the theta equals pi, you can see that this wave function is normalizable. Well, it is normalizable, and not only that, this wave function is exponential of a quadratic in Q1 and Q2. Now there is a very well-known theorem of Hudson, which has been used repeatedly and very successfully by Simon, Sudarshan, and Mukunda. And it is the fact that the only positive definite Wigner functions are those which correspond to wave functions which are exponentials of quadratics. So in particular, this wave function being exponential of a quadratic, it is guaranteed that the Wigner function is positive definite. So no matter how large R you, of course, R going to infinity gives you the Sikh limit, Sikh EPR limit. But if you remain with R finite, however large, you have a positive definite Wigner function, and therefore a classical description of the quantum probability densities of position and momentum. Bell then derived local reality inequalities on temporal correlations, which are of course independent of which wave function you have. Generalizing Bell's argument, only slightly generalizing his argument, if I have spectral decompositions of the operators, of the commuting operators A1, A2, I can construct the commuting operators B1, B2, which have the eigenvalues +1 and -1. You can see that if lambda 1 belongs to the region I1, this projection operator is +1, then B1 is -1. On the other hand, if this projection operator is 0, then B1 is +1. Similarly for B2. And then he constructed this correlation function, the time-dependent correlation function, which is defined as expectation value of B1 T1 and B2 T2 of these two commuting observables. And if local reality holds, they must obey the Bell CHSH inequalities. Bell then showed, he constructed a wave function for which the Wigner function has regions of negativity, and he showed that these inequalities, the Bell CHSH inequalities, are violated. So maybe you might think that this is the end of the story, that the pure wave function does, or in the regularized version, does not violate the local reality. But things which have negative Wigner function might. But this is not the end of the story, because it was realized a few years later by Banaszek, this is a Polish group, Banaszek, Wojtkiewicz, and others made the surprising discovery that for certain other operators, which are displaced parity operators, the Einstein-Bell locality inequalities can be violated by the two-mode squeezed vacuum state, in spite of the fact that the state has an everywhere positive wave function. So this is the continuing story, that the Wigner functions provide you with a classical description of probability densities of Q, P, or their linear combinations like alpha Q plus beta P, but not of general quantum observables. And these observables actually are not difficult to measure. The experiments have been done, and it has been shown that locality inequalities are violated by the regularized EPR wave function. So I wanted to ask a different question, not the question about the Wigner function versus locality, but a question about the contractive or expanding states in quantum theory with local reality. Now the interest in contractive quantum states is actually quite practical. Let me give a few lines on that. So coherent states, of course, are neither expanding nor contracting, but an exception to the nearly universal expanding of wave packets was noticed by Yuan in 1983, and he called them contractive states. And they are very useful because they have been found to be useful in the detection of gravitational waves. In order to, I'm sorry, I'm doing this repeatedly. In order to detect external disturbances such as gravitational waves on an observable of a quantum system, the size of the disturbance must be large compared with the intrinsic quantum fluctuation of the observable. We may prepare the system with a very small uncertainty of the relevant observable. But quantum dynamics can lead to increase of this uncertainty with time. For instance, for a Gaussian packet, we have this well-known expression where XCPT are the Heisenberg operators.
There should also be x and 0.
Sorry?
Sigma square of x must be.
Here is sigma square x0, and dimensionally it is correct. Okay. Okay. So it's like the classic spreading of wave packets for the Gaussian packets. And moreover, the smaller we make sigma x0, the larger the uncertainty principle leads to larger sigma p0s. So the faster growth of sigma xt with time if we start with very small initial packets. Moreover, in fact, during discussions about gravitational measurements, some people claimed this formula to be the standard quantum limit on the spreading of wave packets, namely that the right hand side is a limit for how much, well, let me go to the next slide, it will make things clear. So they called it the standard quantum limit, that the spreading must be bigger than what they had there. However, I obtained recently a formula which sets a rigorous limit for sigma square xt in terms of sigma p0 and sigma x0. And you can see, of course, if this Tm was not there, it would be the usual formula. But because the Tm is there, then you see that this is a quantity which has a minimum at t equals Tm over 2. And what I found, what I showed is that these are maximally contractive states. This is a rigorous inequality. So the maximally contractive states are, in fact, the UN states, which I have exhibited here. The only thing that you need not read the thing at all. The only thing I want to notice here is that this state, the contractive state, obviously a non-classical thing, nevertheless has a positive Wigner function because it is the exponential of a quadratic. Now for multimode photonic states, the new criterion of classicality, namely local reality, can be investigated. And this is what this is the new thing I report today. I present rigorous quantum limits on the accuracy of monitoring higher order quadratures of quantum fields. And I ask, do this corresponding states also exhibit a violation of EPR Bell local reality? So for this, I look at the time development equations for a multimode Hamiltonian of oscillators. So these are all well-known things and very simple things. So the AK of t has this kind of time development, and AK to the n has this consequent time development. And I call capital Q and capital P the Hermitian operators corresponding to this product of AK to the nk. Then using this standard notation of this for the standard deviations, one can see that the Heisenberg equations imply expressions for sigma square qt and sigma square pt in terms of the original uncertainties, and the new thing, in terms of the covariance of delta q and delta p. Here are the explicit expressions from which I want you to notice two things. First of all, if sigma square q is equal to sigma square p, that is the initial standard deviations are the same, and if the covariance is 0, then the time dependence disappears. because I get here sigma square q plus sigma these cosine square theta plus sine square theta gives me 1. So there is sigma square qt becomes independent of time. So there is coherence if sigma square q equals sigma square p and the covariance is 0. Now it tells us something more. For instance, if delta q delta p is negative, the covariance is negative, then for early times sine of 2 omega t positive, I have a contractive state. Sigma square qt is starts decreasing with time, because the other terms are quadratic, the other corrections are quadratic. So I will here is some formalization of the coherence condition which I skip now, because I want to say at least a little bit about the local reality constraints. So from the Schrödinger-Robertson uncertainty relations, it's possible then to derive a limit on the covariance. And the new feature here is that the commutator time term on the right hand side is not a constant. It involves expectation values of powers of number operators. Now you don't have to read all this, it's just to say that it exists. If you work it out, this expression is product of these number operators and minus this number operator. So it's some function of the number of operators nk and the powers nk to which they are raised in the definition. So with this uncertainty relation, we are all set to prove, we prove that the covariance has an upper limit given by the left hand side. And these then are our maximally contractive, these lead to the maximally contractive and the maximally expanding states. So here are the two relations I have. I have put them both for Q and P, but you can read just one of them. They are quite similar since they are for the oscillator type things. So you see here that just like the case of the single particle, I have another, just this number is different, but the formally the relation looks similar. And these bounds are saturated for states in which the bounds on the covariance are saturated. And these states are very simply seen to be those states in which, now here, this equation some people can read if they are interested in following the work. If psi, oh I'm sorry, there is no ket here. Psi is the operator which is ak raised to the power nk, and the ket psi are the states in which obey psi, ket psi is lambda psi dagger psi, where lambda is any complex number. Now for simplicity, I take the case of only two modes, psi equals a1, a2, and I seek the most general solution of the state psi in the number basis, where m refers to the eigenvalues of a1 dagger a1 and n refers to the eigenvalues of a2 dagger a2. You don't have to read these equations. This is just to say that these equations are easy to solve. Yes, I come. So here is then the most general solution, the most general contractive state, which is given in terms of the eigenvalues of the two number operators here, and it contains arbitrary constants C00, C0n, Cn0, and some numbers here, GN0, GNR, etc., which can be computed explicitly. But the main thing is it has these arbitrary parameters. So it is not one single state, but it's a family of states. And in particular, to exhibit to you at least one of them, suppose I take all CM0s to be 0 and all C0n's to be 0, then I get the simple state which is expanded in terms of the number operator eigenstates. And you see that they contain only even numbers, only even occupation numbers. And this state can be seen to be normalizable provided the magnitude of lambda is less than 1. I think I have nearly run out of the time. So this is just for you to say that if you get interested, here are the explicit expressions for the pseudo spin operators which I have constructed in order to construct analogues of the Bell CHSH inequalities. And what we find is that expectation values of sigma 1 dot A, sigma 2 dot B can be explicitly calculated for that state. And it can be seen that if lambda goes to 1, that is the limit in which the state tries to become unnormalizable. In that limit, capital X tends to 1. And in that limit, it can be seen by choosing angles theta A, theta B, etc. It can be seen that the Bell combination of correlations can reach twice square root of 1 plus x squared. And since x can reach 1, therefore this right hand side can reach 2 square root of 2. That is, the maximal violation of local reality is reached. And so we have here a non-EPR continuous variable state that can exhibit maximal violation of local reality and also be useful for gravitational wave detection. Now, experiments, we need to be able to prepare these states and to be able to measure these correlations. There is just something else which I have not put on these slides, just one line statement I can make. One can also calculate the corresponding expressions for the states in terms of the quadratures Q1, Q2. And it seems to be clear to me that the corresponding Wigner function need not be positive. And therefore, it seems possible that there will be corresponding inequalities of Bell type, the time-dependent correlations of Bell type, which this state will violate. But that work is for the future. Thank you very much.